Okay, let's get into the second part of our atomic structure and chemical bonding topic. And now we're going to look at what I generally refer to as secondary bonding. I probably shouldn't use the word bonding, it's more secondary interactions. But we distinguish between primary bonds, which is what we've been looking at now, ionic bonds, covalent bonds, metallic bonds, and we're now just looking at covalent molecules, those molecular compounds, those small compounds between nonmetals and nonmetals, and we are not looking at the bonds within those molecules, like the oxygen and hydrogen bond in water, but we are looking at bonding or interactions between molecules of water, or between molecules of methane, or between molecules of carbon dioxide. So the next three videos are going to focus on things around this idea of secondary interactions or secondary bonding. We're going to start out by looking at the valence shell electron pair repulsion theory, which really is what determines the shape of molecules. And we're also going to look at the polarity. We've already looked at the polarity of bonds between two atoms. Again, now we're going to look at the polarity of a whole molecule. So not just the polarity of the oxygen-hydrogen bond in water, but look at the polarity of the whole water molecule. Now, we've done already some activities on this in class, so hopefully as you watch through these videos, what we've already looked at will start to make sense. So, valence shell electron pair repulsion theory. Big fancy sounding acronym, VSEPR, but hopefully you can see it's something quite simple. If we go back to what we've been looking at around the covalent bonds and the sharing of electrons to get that full outer shell, and we've looked at something like methane here, where carbon would have 4 electrons, so it would share with 4 hydrogens. Now carbon thinks it's got 8, so it's happy. The hydrogens all think they've got 2, which is a full first shell, so they're all happy. Now the reality is that the shape of methane isn't in this sort of square or this sort of cross type form. That's a 2-dimensional representation. But if you look at it in 3 dimensions, and this is the activity that we did with the matches and the little bit of plasticine to see how far away we can push all these pairs of electrons, because all these pairs of electrons have a negative charge, like charges, so 2 negative charges will repel, they will try and push away, and the shape that we got there was a tetrahedral shape. It formed a tetrahedron, so it's basically made up of 1, 2, 3, 4 triangles, all the same size. So that's the basis for the shape of a lot of small molecules, because generally a lot of them will have 8 electrons in the valence shell, so 4 pairs, the 4 pairs will push away, and this will be like the skeleton of our structure. So let's look at this in a little bit more detail. We'll almost go back a step to some simpler ones. If we think about our electrons surrounding a central atom like carbon in this example, if we have, say, 1 bonded pair, and we have then therefore 3 unbonded pairs, that shape, it might be better to do the example. So an example like that would be hydrochloric acid. We won't worry so much about the hydrogen, although we know that's going to have 2, but the chlorine would have 7 electrons. 1 of those electrons would be in this bond, 1 from hydrogen to give it 8. So the chlorine would have 3 unbonded pairs of electrons, and then there's 1 bonded pair in this bond. Now the shape of that, it's only got 2 elements, so the shape of that would be linear. Might start now at the other end, which is the example I've already drawn there. What about if we have, like methane, 4 bonded pairs no unbonded pairs, that shape, well, which is like the example we've got there with methane that you can see, I won't draw that out again, that shape would be tetrahedral. Now, in between there, let's go back to this one. Let's say we've got 2 bonded pairs and 2 unbonded pairs. And you might remember when we looked at water, that is a bit like the case with water, where we have 6 electrons around the oxygen. One of those electrons from the oxygens is each involved in these bonds, and one from the hydrogens to give it that 8. So we've got these 2 bonded pairs and these 2 unbonded pairs, and there we get a V-shaped molecule. So it's a little bit like the tetrahedral with 2 of the arms, that gives V-shape, and these other 2 arms are empty. So these 2 V-shaped arms give it that V-shape. And then if we've got 3 bonded pairs and 1 unbonded pair, let's look at the example. And ammonia, so nitrogen has 5 valence electrons. 3 of them are shared with each of the hydrogens, 1 here. So there's our 1 unbonded pair and our 3 bonded pairs. Remember, a bond is just a shared pair of electrons. And that gives us a trigonal pyramid. So a lot of molecules are based on those 4 structures. Just looking at one now that's a little bit more complex, but is quite common. If we go back to our carbon dioxide, carbon with 4 electrons around it, oxygen comes along with 6 electrons around it. 1, 2, 3, 4, 5, 6. So to get the carbon now thinks it's got 8, and the oxygens think they've got 8, and the oxygen here thinks it's got 8, and we can draw that structure out more commonly like that. Now, there's probably a hint there that you're thinking it's linear because of the way I've drawn it. But just to explain why it's linear, is you've basically got 2 regions. You've got a region of 4 electrons on this side, a region of 4 electrons on this side. So those 2 regions of electrons are going to repel each other as much as they can. If you've got just 2 things, the best way they can repel is just to push away from each other along a straight line. So that gives us a net result of this structure being linear, as this set of electrons here and this set of electrons all push away from each other. So that is our little lesson on valence shell electron pair repulsion theory. Thank you. And for the final part of this lesson, we want to look at polarity. And here we want to look at the polarity of a molecule. So not just the polarity of a bond. We've already talked about apolar bonds and non-polar bonds, and that being about whether the electrons are shared equally between the 2 atoms making up the bond. So are the electrons shared equally in this bond? Are they shared equally in this bond? That's what makes a bond polar or non-polar. When we're talking about the molecule, though, we are talking about the distribution of electrons across the whole molecule. So in a polar molecule, there's an uneven distribution of electrons across the whole molecule. And in a non-polar, there's not. So how do we go about determining this? Well, firstly, we need to decide, are there any polar bonds? If there are no polar bonds, then it's non-polar. End of story. We don't go any further. If there are polar bonds, we've got to do a second test. We've got to decide, is it symmetric? Symmetric means if you cut it in half, either along the X, the Y, or the Z plane, so whichever way you cut it in half, do you get the same thing on both sides? If it's symmetric in all planes, the X, Y, Z plane if you like, then all the polar bonds will cancel out and it will be non-polar. However, if it is not symmetric, it will be polar. So let's look at a couple of examples. Work them out. So let's start here with oxygen gas. Does it contain polar bonds? So follow along here. Does it contain polar bonds? No, therefore it's non-polar. So, no polar bonds, therefore non-polar. End of story. Easy. Let's now look at water. Does water contain polar bonds? Yep, it does contain polar bonds. So, then we come down here to the symmetric box. Is it symmetric? Well, if you cut it through there, through the middle, yes, it is symmetric. If you cut it through in the plane of the page, it would also be symmetric. That's a bit harder to picture. But if you cut it through the middle this way, you can see it's not symmetric. There's an oxygen at the top and there's a hydrogen at the bottom. The oxygen, because of our polar bond, has got the slight negative charge. The hydrogens have got the slight positive charge. So you can see that this end of the molecule is going to have a negative charge. This end is going to have a positive charge. So there's polar bonds and non-symmetric. Therefore, it is a polar molecule. Carbon dioxide. Does it have polar bonds? Yes, it does. The oxygen is more electronegative than the carbon, so it does have polar bonds. Is it symmetric? Well, if we cut it in half that way, it's the tame and the top and bog. It is symmetric. If we cut it that way, it's the same in that direction. Plane of the page was the same. So here, all these polar bonds, if you like, are cancelling out. So overall, it will be non-polar. So yes, it has polar bonds, but it is symmetric therefore those polar bonds all cancel out and it is non-polar. So I wonder if it's just quickly make a note of that. It's symmetric, so therefore polar bonds cancel out. Sorry, it got a bit messy there. But that is the process for working out whether a molecule is polar or non-polar. Thank you.